speaker is on a mission. He is here today to prove something, and that is pandas.DataFrame is one-dimensional. So if you love pandas, I mean, obviously you do, this is going to be your go-to talk for everything about pandas. So give a warm round of applause for James Powell.
Okay, folks, we're short on time, so we'll go through this very quickly. This is how dimensional is pandas data frame anyway. We're at PyData Amsterdam. It is Thursday, September 18th, 2024. My name is James Powell. You can connect to me on LinkedIn. I basically accept every connection request, even if I don't know you. So if you want to bump up your follower count, I don't really care one way or the other. Let's go. Okay, here's my assertion. A pandas data frame is one-dimensional, even though the pandas docs say it's two-dimensional, and a lot of people talk about it as though it's two-dimensional. It's not. In fact, my assertion is that all of pandas is really just one-dimensional data, and there's no real dimensionality beyond one-dimensional data within pandas. This talk is my proof. Now, bear in mind that the standard for this proof is not particularly high. Proof might be a little bit much of a word to use for what you're about to see, which is going to get a little bit wild. But we'll start off with a little bit of terminology like any good proof starts. And so we'll see that this terminology is largely intuitive despite being kind of made up completely. We'll start with some terminology you're all mostly aware of, things like homogeneous, which means of the same type, as distinct from heterogeneous, which means of different types. And if we think about this in practice, we can think that in terms of pure Python, a Python list, like this list that you can see here, is homogeneous. In fact, it turns out that in almost all of our use of a Python list in Python, the list is almost always going to be homogeneous. We can imagine what this might look like in our actual code. At some line of our code, we create a list that looks like this. Some other line of our code, we use this list. And in fact, we can even mark out these 2 points of our code. We can talk about the define point and the use point. And the homogeneity of this list is fairly obvious because in between that define point and that use point, you could perform all sorts of operations to this list, add elements, remove elements. Well, the use point can only look in a certain way in order for it to be ensured to be correct, specifically looping over each element of this and doing largely the same thing to every element. If we were to look at some code and we had a Python list and it looked something like this, we'd say, that's really weird. What's so special about the 3rd element? If you had some code and it looked at a slice from the 3rd to the 7th element, you'd say, what's so special about those elements? Do note that this doesn't mean that the list doesn't have modalities, because if you looked at some code and it said, look at the 0th element of this list, you'd say, oh, there's some special modality here. There's something special about the first thing we collected. Similarly, the last thing we collected, and in a very similar sense, the slice up to the first 3 things. We might wonder why the first 3 things are of interest, but there's clearly some initial modality here, similarly with some final modality that we can see here. Even if we were to look at some code like this, very simple code that just looks at windows of overlapping size of 3. Here, this is just a generalization of itertools.pairwise. We'd say, OK, that makes sense. We want to do, say, some sort of rolling average of this data, looking at overlapping windows of 3 values. If we think about how the list is used, we define it at some point, we use it at some point, and not only do we use it at some point, we basically loop over each element and do the same thing to each element. This is why we can say very, very confidently that the list is almost always homogeneous, except it's actually, in pure Python, almost always loosely homogeneous. And we have to introduce a little bit more terminology here, the idea of loose versus strict homogeneity. Because if we look at this list is strictly heterogeneous. It's got an integer, it's got a Boolean value, it's got a float value, and a complex value, but we can still loop over every single element and do the same thing to each element. And in fact, Python very much supports this. This is basically the whole idea of things like duck typing. It is very unlikely that we'd ever see code that looks like this, where we loop over each element and we determine what to do based off of what the type of the element is, in part because this code won't even work, because in the Python standard library, we have the fractions.fraction and the decimal.decimal, and there's no chance that we'll be able to remember all of the different subclasses of numeric values and to be able to dispatch based off of them individually. In fact, we can actually do this. In the Python standard library, there's a numbers.number, and you can assert that this is an instance of a number.number. I've never actually seen anybody do this in real code. I don't know who uses the numbers.number module, but it does exist. But it doesn't really matter, because if we look at how these things are implemented, it turns out that we can compute things like the complex conjugate on all of these data types. Let's take a moment here. Complex conjugate is not an interesting thing to ask about any of these values except for the complex number. What is the complex conjugate of a fractional value? It's just a value itself. And yet, Python is designed in such a way to support the ability to do this so that we can treat this list that is strictly heterogeneous as though it were homogeneous, thus loosely homogeneous. By the way, for those of you who are interested in joining us for the pub quiz, here is a sneak peek at one of the pub quiz questions. What operations in the Python's built-in numeric types are unique to just one type? This is a sneak preview of a question. But when we think about this homogeneity, one thing that we can think about is strict homogeneity actually of the same type. Loose homogeneity can be treated as though it's of the same type. But there's something that might be a little bit disturbing here, specifically that when we talk about loose homogeneity, it's a bit squirrely of a term, because if we think about it, the looseness of this homogeneity is actually quite subjective. In other words, if we look at this code, we're iterating over every value and doing the same thing to each value, printing it out, but it's very unlikely we'd ever see a list that looks like this in real code. This is a very degenerate form of loose homogeneity. It's loosely homogeneous in the sense we can print out those values, but that's such a broad sense of homogeneity that it's not actually practically useful. So unlike strict homogeneity and strict heterogeneity, which have a very concrete definition, we're dealing with something that's a little bit more subjective and related to how we end up using these structures. This will, in fact, come into use later. If we want to try and draw some parallels, we can talk about strict heterogeneity being of actually different type, and thus, if there is something behind this terminology and something behind this reasoning, then it stands to reason that there must be something like loose heterogeneity, that elements are, in fact, homogeneous, but they must be treated as though they are the same type. And there's a little bit of an intuitive sense that we might be on the right path, because loose heterogeneity also exists in pure Python. That's what a tuple is. This tuple here is strictly homogeneous. They're all strings. But we can't do the same thing to an IP address, that we can do a state, that we can do to a zip code, that we can do a human name. They support very different operations. In fact, this data is strictly homogeneous, but in fact must be treated as though it is heterogeneous. We must treat each of these values, despite being modeled as a string, as though they were different. In fact, if we think about it, if we ever saw some code and it looped over a tuple like this would be very weird. What can we do to every field of a tuple that's the same item? And this is, in fact, why, if we look at syntax in Python, we may know that there's list comprehension syntax, set comprehension syntax, dictionary comprehension syntax, but there's no tuple comprehension syntax. This is not a tuple comprehension, it's a generator expression. Why is a tuple comprehension missing? Because the tuple is almost always strictly or loosely heterogeneous. It doesn't make sense to be able to transform a tuple by performing some singular operation on every value. That's not exactly true, because using PEP 448 generalized unpacking, additional unpacking generalizations, you can actually create something that looks like this, which gives you a tuple. This is the closest we can get to a tuple generalization. By the way, the PEP number, if you forgot what it was, well, it's going to be on the pub quiz too. You could say that this is a degenerate modeling. We're just using a string because it's the most convenient way to represent this data. And in fact, the zip code should be an enumerated value. The IP address could use something like IP address from the standard library. But here, we just turned something that's loosely heterogeneous to something that's strictly heterogeneous. This didn't really change the nature of our argument one way or the other. It turns out that in practice, tuples in Python are almost always loosely heterogeneous. Here's something that's kind of interesting, though. When we think about the distinction between a tuple and a list, we can see that there's a natural distinction here beyond just the homogeneity and the heterogeneity. Tuples almost always represent one thing with many distinct fields, aspects of that one thing, and lists almost always represent many things that are largely interchangeable, where the ordering of a tuple is a semantic ordering, where the element exists in the tuple is what it means, and the ordering of the list is just the ordering in which we process those. That's why we can sort a list, but we can't sort a tuple. It's meaningless to sort a tuple, but it's very meaningful to sort the list. You're just changing the order in which we process these elements. You can reverse a list. What would a reverse tuple mean? It has no actual conceptual meaning. Now, what's really interesting when we think about the built-in structures in Python is there's actually two dictionaries in Python. There's a structural dictionary and a data dictionary. There are two different ways in which people use dictionaries. A structural dictionary looks something like this. Here we have names and values, strings and integers, and this is maybe a slightly more self-descriptive modeling of what we might model as a tuple that, as this code begins to evolve, might turn into something like a class, in this case a data class, and if we dig deeper into that class and we ignore slots, which we should all ignore, it's a very boring topic, we can see that under the covers, this object actually models its instance state as a dictionary. There's a very close relationship between the structural dictionary and the object. This is only one side of the dictionary, because this is, of course, how we'll operate it. We'll pick out individual fields, perform an operation on it. And when we look at the structural dictionary, we'll see that it's typically homogeneous on the keys, well, that's more of a convenience, and heterogeneous on the values. But the other side is a data dictionary. These are the types of dictionaries we use in another formulation, very distinct from these structural dictionaries, where you can see that the keys are homogeneous and the values are homogeneous as well. This data, as the code evolves, won't turn into an object. It'll turn into something like a pandas series. In fact, we can think that a Python dictionary is a 0th order approximation to something like a collections.counter, which is a 1st order approximation to something like a pandas.series. Here is how that code would evolve. It's a very different entity despite using the same built-in type. When we operate on this, what do we do with the data dictionary? We don't know how many elements are in this dictionary. It's data after all. So we'll loop over all the values using a d.items. We won't select out the values directly by their key, and we'll perform some operation on the keys and the values. You can see why it would be the case that this would be almost always homogeneous on both. Here we can see data dictionary, homogeneous on keys as well, again a convenience, but more critically, homogeneous on the values. Here we can see a very interesting dichotomy, and I think that's something that arises in many different formulations in our code. The idea of our code having structural components that are fixed, countable, human scale, and not part of the axis across which we automate, and data aspects of our code, which are variable, uncountable at the machine scale, and automatable. For that structural dictionary, it's only going to have a certain number of keys that you can remember what the names of those keys are as you can type them in. But for the data dictionary, it could be of any size. It's actually one of the axes across which we automate. And what you can see here is that these are not really two sides of some dichotomy, but in fact, some spectrum. There is some middle point where it may be ambiguous whether we're talking about a structural entity or a data entity. But setting that aside, enough about Python. Because honestly, many of us are pandas users, or many of us work on LLMs. What do we really need to know anything about Python for? After all, Python, I guess, is involved somewhere in there. So let's instead talk about NumPy. And when we talk about NumPy, one of the interesting things we can talk about NumPy is the distinction between a NumPy ND array versus a Python list. Because you'll see that when you look at scientific code, it's very often the case that scientific code will sometimes incorrectly use a NumPy ND array when it might be more appropriate to use a list. And in fact, it is a very meaningful thing to have in your code a list of NumPy ND arrays as a consequence of some limitations of using a NumPy ND array. Well, this is one way that we can create a NumPy ND array. And before we talk about its relationship to a list, we can talk about something that, again, I'm not quite sure if anybody actually uses this in the Python standard library, the array.array. I don't think I've ever used this before. I'm not quite sure what this is useful for, but in a very similar sense that a collections.counter might be a first-order approximation to a pandas.series, an array.array might be considered to be a first-order approximation to a restricted computation domain like a NumPy ND array. Well, if we do a little bit of just a canonical analysis of these structures, like we might do here, where we're going to pull in numpy.product, we'll create a python.product, we'll create some random data. We do a little bit of timing, we can see some of the effects of these things. For example, if we take two Python lists and compute their dot product, we can see that the sortedness of those lists, or the shufflingness of that list, actually has an effect. If you think about how a list is actually stored in Python, it is a contiguous block of memory that stores references to the underlying data. So when we perform the shuffling on this data, we're actually triggering some sort of cache locality misses that are really penalizing us for all of that pointer chasing. And we can see that very directly here from the PyDot operation before and after we perform that shuffle. When we do the same thing on a NumPy ND array, we can see that it's invariant to that shuffling because it is truly contiguous data in memory with no additional layer of pointer chasing. And if we do the same thing on a array.array, we can see the array.array is actually contiguous in memory, machine typed, and just slightly more efficient than a list.list, but the only way for us to actually operate on this thing is to pull those elements out. So there is still some cost that we're paying in crossing the restricted computation domain boundary. In other words, in taking the elements inside that array.array and pulling them into the Python domain and constructing Python integer values from that. Setting that aside, we can see some parallels between the NumPy ND array and the list, where the NumPy ND array is strictly homogeneous. In fact, it's not only strictly homogeneous, it's almost always machine typed. And the Python list is loosely homogeneous, and it's richly, extensively typed with arbitrary behaviors that you can implement by extending the Python data model. Now, another interesting distinction we can see between the NumPy ND array and the Python list is that a NumPy ND array is fixed size. After all, NumPy ND array is a interpreted view of raw memory. What we have is a pointer to some block of raw memory, its size, its stride, its D types, and that's all our interpretation of that memory. A NumPy ND array has no distinction between size and capacity, whereas a Python list is dynamically sized. You can grow it in place. It has a distinction between its size and capacity. In fact, if you take a list and you grow it, and you track how much memory it's using, and you take the second derivative of that, you'll see it's constant. You can get a little bit of a sense for how that actually works. Every time you get to the capacity of the list, it just doubles its capacity. There's a distinction between size and capacity here. Now, I told you that you shouldn't read too much into the word proof here, because basically the standard of proof here I have is if it rhymes, it must be true. It turns out that a NumPy ND array is fixed size but dynamic shape, and a Python list is dynamic size and fixed shape. Isn't that convenient? Well, what do we mean by dynamic shape versus fixed shape? Well, it turns out that when we're talking about NumPy ND array, it's an interpreted view of raw memory. So we have a block of raw memory with a D type associated with it. And we just swap out that interpreter layer to take something that's originally 2 by 3 by 4 and just say, let's look at it as though it's 24 by 1 or 12 by 2. Whereas if we have something like this as a Python list, some people might casually call this a two-dimensional list, but it's not a two-dimensional list. This has no real two-dimensional meaning because we can change this data very slightly. This has no dimensional meaning. We can't just add an element off to the side. We can even nest these. This is grouped data. This is nested list. Lists are fundamentally always linear. They're only capable of being nested in a way that, say, NumPy and D arrays are not. In fact, when we talk about the list, we should see that the list is always linear but nested. Lists are fundamentally one-dimensional entities. Now, when I first came up with the idea for this talk, one of the things that really made sense to me was the thought that if I have a flat sheet of paper and I put a banana on top that doesn't make it two-dimensional, I don't actually know what this was supposed to mean, but it really made sense to me at the time when I put this talk together. Maybe it might make sense to you sometime after. If we take a look at why we might, or how we might describe the dimensionality of these structures, we might say that a NumPy and D array is two-dimensional, or three-dimensional, or n-dimensional, because the number of coordinates we use to access a singular scalar value, well, this is a three-dimensional NumPy and D array, there's 3 coordinates used. And if we look at the equivalent Python list, we might say, well, aren't there 3 coordinates here as well? Isn't this list three-dimensional? But there's a slight distinction here in that, one, we're not sending all 3 coordinates to one operation. We're doing subsequent operations, pulling out one result and then doing an operation on that result and doing an operation on that result. And also, if we were to follow that line of thinking, the idea that the dimensionality is determined by the number of coordinates, we can come up with some very ridiculous answers. Like, for example, both of these Python lists are actually two-dimensional. Because here, when I'm selecting the 0th element of x's, what I'm actually doing is I'm selecting which value I want, and then the 0th dimension. I have 2 coordinates here. This must be two-dimensional. Clearly, the number of coordinates that are used to access the data has no real relationship to any meaningful sense of what the dimensionality of this data would be. In fact, if we look at this and we squint a little bit, we can see that there's an interesting distinction between the idea of a structural coordinate and a data coordinate, where in fact, which of the 2 lists we wanted would be a structural coordinate, and the element within that list would be a data coordinate. But we'll set that to the side, because that opens up a larger frame of discussion. Now is a good time for us to talk about pandas, because the idea of structural coordinates and data coordinates actually appears in pandas. If you think about it, it's almost always the case that the values in your index are data coordinates, and the values on your columns are structural coordinates. You know about them ahead of time. They're fixed in number. There's only so many of them, and you refer to them specifically by name manually in your code as opposed to automating across them. That's not always the case, but it's almost always the case for most pandas code. For example, if we have something that looks like this, here we have a pandas series indexed on date values representing some kind of temperature measurements, and it looks something like this. Well, I'm not going to tell you that this is two-dimensional. Clearly, it's one-dimensional data with an index associated with it. But the problem is, when we take this temperature data and we put it across from humidity data, and you look at how we access a single value from this, you can see that there are 2 coordinates. We first access which element on the index and which element on the columns. In order to get the singular value, we can use a dot lock with 2 coordinates, or we can use a dot at. And when you look at the structure of this thing and you look at how the pandas documentation talks about this thing, it's going to say this is two-dimensional data. This is not two-dimensional data. This is 2 data sets that are each one-dimensional that have just been brought together and index aligned. This is not altogether too dissimilar from our example of picking which of the 2 lists we wanted and the value within that list, which I don't believe is sufficient to call this thing a two-dimensional structure, even though it may be the case that we might try to interact with this value in this fashion. Now, we can rewrite this in a couple of different ways, accessing a singular value by looking at the column and then looking at the value. And in fact, this is probably the most common way that you would actually access this. Here you can see this is very clearly a structural coordinate. We're assuming that nobody's going to catch an attribute error off of df.temperature. So we have a very strong assumption in this code that that must exist, it always exists, and if it doesn't exist, there's something fundamentally wrong with this code. This is not a data coordinate, and this is not a two-dimensional structure. In fact, if we think about the structures in pandas, we can say that a pandas series is a one-dimensional, strictly homogeneous structure. Intra-column on a data frame is also, each of them is one-dimensional, strictly homogeneous, and inter-column, from column to column, it's very commonly heterogeneous. It's not two-dimensional data. If some of the data is of one D type and some of the other data is another D type, there's no way for us to do operations across that data. We can only do operations down the columns in one way. In fact, if we think about it, a pandas series is one data set, and a pandas data frame is how we represent multiple data sets that are indexed in a very similar fashion. It's index-aligned one-dimensional data. In fact, we can see that there are mistakes that are made in the pandas API as a consequence of this. For example, if we have this data frame and we do a describe on this data frame, we get some output that looks like this, but this output is totally meaningful. The first value is the count of non-NaN values 3.0? What does a count that's a floating point value even mean? What does 3.5 as a count actually mean? And in fact, we can even see that there are real errors that occur as a result of this, because if you look at the min and the max value, as a consequence of having to force these up to a float D type, we've lost the precision of storing these. And so for this particular data frame, the max is not guaranteed to be larger or equal to all of the values, and the min is not guaranteed to be smaller than or equal to all the values. That's nonsense. Well, this is a consequence of the loss of precision, because df.describe is not really a very well-formulated thing. In fact, even if we try and do things like pivot this df.describe to transpose it, we also get something that's meaningless. In fact, df.describe is not really a well-formed operation. We really shouldn't use it for anything serious. It's good for debugging, but that's about it. Note that pandas privileges operations down the index. This is a very core idea of pandas. In fact, to the point that in current versions of pandas, you can't even group by on column axes anymore. It tells you instead you have to transpose and group by. This is a terrible idea, by the way. This is a mistake from the pandas developers. They're going to have to fix this, because sometimes you do need to group by across columns, and transposing the data is going to cause D-type changes that are going to eliminate precision, or they're going to cause issues with how you represent the data. But fundamentally, my assertion here is that a pandas data frame is usually index-aligned collection of one-dimensional, strictly homogeneous data. Pandas series is one data set, and a pandas data frame is multiple data sets. But the real question is, who even cares? I don't know. You're all here. Maybe you do. Let me show you two examples in the time that I have remaining for where mistakes are made as a consequence of misunderstanding the core dimensionality of the data. The first is something that looks like this. Now, there's a lot of code here, but at its core, what we have is some pricing data. We have some pricing data stored in an X-array data array on dates and tickers. I saw a post just the other day where somebody said, look how great it is that X-array can be used to model common data. I agree. X-array is a fantastic tool. Common two-dimensional data, like prices for tickers and dates. No, this is not two-dimensional data. And the reason it's not two-dimensional data is companies like Blockbuster came into existence in 1985 and went bankrupt in 2010. If you have 50 years of ticker data, that means that we have 25 years of NANs extending out to infinity for names that no longer are in business. This is not two-dimensional data. This might look two-dimensional, but it's just a coercion of fundamentally one-dimensional data into a two-dimensional structure with all of the consequences thereof. What this, even though we might have two coordinates in order to access these values, what this really is one-dimensional data with a hierarchical index associated with it, the proper modeling for this data, especially because it's very likely to have gaps, and will almost certainly have gaps in the real world, is as a one-dimensional multi-index structure. Now, I want to talk about the second example, and we'll get through this very quickly. It's about pandas.series.stack, which is a very interesting operation because it's one of the few operations that people don't realize has real semantic meaning in pandas. I'll remind you what it is. Pandas.series.stack and unstack are about taking a level of a multi-index and turning it into some columns. So it means that for some data that looks like this, you unstack it to turn it into something like this. You took that level of that index and you turned them into columns. In fact, there's a very interesting relationship between stack and group by. A group by ag operation is equivalent to an unstack apply stack, assuming monotonic, non-duplicated index values. And in fact, a really surprising thing is you can sometimes get significant performance improvements in pandas by using the unstack apply stack. For example, in cases where you have a group by with a rolling operation on a time series window of indeterminate or of dynamic size. Note that a pivot table in pandas is also the equivalent of a group by unstack operation. This is distinct from a pandas data frame melt, which has no semantic meaning. For a reminder, what melt does is it takes data that looks like this and turns it into something like this. This here is actually two data sets. This is very common if you look at United States government Bureau of Labor Statistics data where they have the dates going out on the columns. This is a result of how they store this in Excel. There's actually two data sets here. There's one data set, this base column, and everything else that needs to be pivoted down. All melt is doing is data cleaning to turn this into two data sets. It's not a real semantically meaningful operation. Well, if we think about it, what stack is about taking one homogeneous data set and saying, oh, there's some ambiguity about the homogeneity of that data. In fact, we can turn it into multiple data sets. I'll show you another example, and something that I used to do that's actually strictly wrong. When we model trading data, not pricing data, we have the trades that we might trade as part of some portfolio analysis. We might model as a data frame with the prices that we traded at and the volumes that we traded at. And when we want to do something like compute our P&L, what we'll do is we'll compute the cash value by taking the prices and the volumes. We'll compute the market price by getting the actual prices. We'll compute the market value by by multiplying times the volume. This is, by the way, wrong because prices are not linear. And we'll compute the P&L by adding the cash to the market value. And this seems fairly straightforward until we realize that largely pricing data is going to be a two-sided market, and we have to deal with the buy side and the sell side. And the buy side and the sell side is going to be determined by the aggregate position that we hold. So what we have to do is we have to first compute the cumulative volume and determine from the cumulative volume whether on the buy side or the sell side for our cumulative position, and then compute the market value in our P&L. And this just starts getting messier and messier and messier. Well, we have a structure here. Does it store deltas? Does it store states? Does it store individual trades or positions? And we're getting more and more confused trying to represent this data because we fail to understand the core dimensionality of this data. Additionally, there's certain things we simply can't represent, like multi-leg trades. We're here in the Netherlands. If I want to buy certain assets like oil, I cannot do that denominated in euros. I have to trade into US dollars and then into the asset that I want. And there's no easy way to represent it in this particular structure because it turns out that the multi-leg suggests that the coordinate system that we have here is actually a data coordinate system, not a structural coordinate system. But remember that homogeneity is subjective. When we talk about pandas series unstack, we're talking about turning one data set into multiple data sets. When we talk about this, it makes a lot of sense because you always have done an unstack plot. When you think about matplotlib, matplotlib says one data set is one line. Sometimes you have one data set that's one series, but you want to turn it into 3 lines. You unstack a layer of your index, and you get 3 lines. It's about taking one homogeneous data set and saying this actually, from a different perspective, is multiple homogeneous data sets. And if we look at this data, we can see that the trades data is subjectively one-dimensional. It's one-dimensional if we assume that one of the dimensions is on a hierarchical multi-index based on the asset. And in some cases, we might actually want to split that into multiple data sets using group by operations or stack or unstack. In fact, the proper way for us to model this is a series of a multi-index with a datetime index, a categorical index, not on the ticker, but on all of the tradable assets, including currencies, and a float or an int for the delta volumes. It's questionable whether this should be a float or an int because obviously we can't trade in fractions of pennies. There's a certain minimal tradable size. So really that's integer value, but for convenience, mostly we'll represent this as floating point value. Do note that one other thing that's limiting this example is prices are not linear. But that's not that much of a distinction because most of the time people just kind of assume prices are linear and it mostly works. But a more important thing is prices aren't real. There's no such thing as a price. Just because I'll buy something at a certain price or sell something at a certain price doesn't mean I'll actually do that when it comes to trading. Cash is real. In fact, if you remember anything from this talk, remember this. There are only 2 real things in this world. The first real thing is physical. It is money. Money is real. The second real thing in this world is spiritual. Love is real. It is real. It is the only thing that is worth living for. Do not intersect the 2 of these. The love of money is the greatest folly you can ever experience in your life. But setting that aside, the correct modeling for this trading data is a one-dimensional series of all the assets indexed on these things that looks something like this with additional asset values for the USD trades. And what we would do is, using a little bit of contortions that we have, for example, the extension of index operations in pandas. Here, this a little bit, you may have seen this before. What we can do is we can pull in the trade number, and then we can define a way to execute a trade, which is just finding the price and creating cash flow rows of this. We can define a way to liquidate these trades, which is just swapping the volumes at a different date and then creating the cash flows for this. And we can compute positions in a very simple way. It's just the cumulative sum grouped by asset. We can compute market values. It's just the liquidation of this group by asset or the concatenation of our trades and the other side of that trade group by asset and cumulative sum. We can compute the P&L in a very direct way. We can model anything. We can model nonlinear prices, we can model multi-leg trades. Everything just works because this data is one-dimensional. And because this example only uses the most properly formulated structure in pandas, a pandas series, pandas data frames are not really well formed in this sense. They're a way for us to conveniently collect index-aligned data. But pandas series are a well-formed entity because in pandas, we really only ever want to operate on one-dimensional data. That's why we're using pandas. Pandas is one-dimensional. Thank you very much.
Questions?
All right. Nice one, James. So regarding pandas deprecating axis equals 1 in group by, you said that you don't like having to call the transpose yourself. Pandas was already doing this under the hood for you in many cases, though. Are you sure that people should have such an expensive operation done under the hood automatically for them, rather than doing it explicitly themselves?
So there could be cases in which a pandas data frame actually has data coordinates on the column. I've done this before. For example, if you do something like a NumPy mesh grid in order to create the underlying data, then your columns and your index will be identical. So you'll actually have data coordinates on both, in which case a group by down the index is going to be identical semantically to a group by across the columns. You should be able to do a group by across the columns without some contortion or without necessarily forcing a D-type change by forcing the block manager to change things. If under the hood the group by axis equals columns did a transpose internally, that's the core of the mistake. And changing at the surface level is not really the problem. But fundamentally, we should be able to do group bys across columns in the rare case that we happen to have actual two-dimensional data that happens to be modeled in pandas, despite that being the vast minority of actual cases. Since pandas is, this thing is actually fundamentally API-wise, convenience-wise, how people actually use it one-dimensional. Does that answer your question? No, it doesn't. Okay.
Sure, I mean, would you be okay with deprecating it in the general case, but just still allowing it in this minority of cases that you described?
Let me also be very clear one thing. Pandas is a fantastic tool with a very coherent design and an incredibly inconsistent API with lots of weird fast paths that can be very frustrating to remember how everything is spelled.
Yeah.
And some complaints that I might have about pandas are not meant to be negative. They are meant to be an inspiration for maybe you all can join the sprints and contribute to the library to make it better. Or just use polars, I don't know, just whatever you want to do.
Agree.
Okay. Index alignment is really useful. And one thing that I think is important is, despite how fantastic of a tool and how exciting of a tool polars is, understand that if you are using a tool, if you're trying to do an analysis that requires index alignment, and you're recapitulating the index outside of a structure that provides you with an index, you're going to have a worse time than if you just use pandas. If you don't care about indices and there is no notion of index in the fundamental representation of the analysis, fine. Use NumPy, use polars, use whatever you want.
Last question.
I feel like this is more of an observation than a question, but I really feel that if you think of data as a one-dimensional series of index-aligned data, I really feel you would really enjoy like a normalized relational data model. I really feel that aligns with your mental model of it.
Because we're saying when you look at the normalization forms, when you get to 5NF and 6NF, nobody remembers past like 3NF, and most of you don't even remember that. All like 5 and 6NF mean is really, really skinny tables.
Yeah, that's essentially how I think of your mental model, if that's all right.
And basically, you're then just doing foreign key operations. That's what the index alignment is. Foreign key, different joined operations with. But do bear in mind that the index alignment modalities are not necessarily equivalent to Cartesian product, which is the default modality here, because you have things like the sortedness and the uniqueness of the data frame affecting whether or not you do Cartesian product or you do exact matching. And there's a couple of these weird like edge cases that nobody can remember.
There's a lot of implicit joins.
Yeah. So I guess maybe. So use pandas if SQL is too recent of a tool for, I don't know. If it's too cool of a tool for you to use. Pandas is great. I love pandas. It gets a lot of real, honest to goodness, useful work done. Sorry, it makes me a lot of money. I don't know that the work I do is useful, but at least it gets me a lot of real useful paid work done.
I'm sure most of you have more questions and want more of James Powell, so he will be around also at the pub quiz if you made notes for the 2 questions. Give it up for James Powell.
Thank you, everybody. Oh, thank you.